So now we are very good at calculating work, and you might wonder, why are we spending so much time calculating work? Well, there's a very, very useful theorem called the work energy theorem. And that theorem says that delta K, that's our change in kinetic energy, is equal to the net work done on an object. So delta K, what is delta K? That's the change in kinetic energy. That's K final minus K initial. And what is K final? How do we calculate K again? It's since K is 1/2 mv squared, K final is simply 1/2 mv final squared, and K initial is simply 1/2 mv initial squared. So our change in kinetic energy, which is equal to 1/2 mv final squared minus 1/2 mv initial squared, that change in kinetic energy is equal to the total work done on an object. How do we calculate total work? Well, you can either calculate the net force and then figure out how much work the net force does, or you can find the work done by each individual force and then add them all together to get the total work. Okay, you can do either one. And this is very useful, and this equation is going to be super, super, super useful because, as you can see, it lets you take information about forces and figure something out about how the speed of an object changes. Okay, so let me just remind you the way that we used to solve problems like this, the old way that we've done previously. We would draw a free body diagram, we would find the net force, we would set the net force equal to ma, we'd solve for the acceleration, and then we would use kinematics to find a new velocity. Or maybe you would use the change in velocity to figure out what your acceleration is, then you would plug your acceleration into here, and you would figure out your net force, and then you would figure out something else about some individual force. That's kind of the old way we solved problems. Now we're going to solve the same type of problems, but just using this single equation here, the work energy theorem. The new way is going to look like this. We're still going to draw a free body diagram because we still need to know all the forces. We're going to figure out how much work each force does, and then we're going to add them all up, get the net work, and then solve for whatever velocity we're trying to figure out. That's it. So let's do two quick examples, and then we'll do some problems. So press pause, read through this, and try to get an answer. Okay, so the correct answer is 14 joules. Let's look at how we got there. This is a force that changes. This is a variable force. It is not a constant force. So to figure out how much work is being done, I want to know how much work is being done because they're asking me about kinetic energy. So to figure out how much work is being done, I can either write an equation for this line and then integrate that, or I can take the area under the curve. Okay, let's just recognize I'm starting off with 2 joules of kinetic energy. The way that kinetic energy changes depends on how much work this force is doing, and I can figure out the work the force is doing by taking the area underneath here. Since this is my net force, that's what they're telling me, this area is going to represent the net work, the total amount of work. So let's find the area underneath here. That's just going to be 1/2 times my base, which is 4, times my height, which is 6, or 12 joules. So this force that gets bigger and bigger and bigger as the object moves does 12 joules of work. The object started with 2 joules of kinetic energy, then an external force does 12 joules of work on it. My total work is equal to my change in my kinetic energy, so I can find my final kinetic energy is 14 joules. Let's do one more, same initial stuff, except now we know how fast the object is going at this position, x equals 0. And I want to know how fast is it going when it reaches x equals 4. So press pause, take some time to work through this and see what you get. The correct answer here is 3.46 meters per second. Let's see how we got that. From the previous problem, I calculated that the area underneath here gives me the net work, which is 12 joules. And I know that my net work is equal to my change in kinetic energy. Here, instead of writing my change in kinetic energy as K final minus K initial, I'm writing my K final as 1/2 mv final squared, and my K initial is 1/2 mv initial squared. Then all I need to do is plug in the numbers, and I can solve for V final.